All right, thank you very much. So yeah, I did this work, PicoEMP, which is designed to look at a really low-cost electromagnetic fault injection platform. But I think more interestingly, also to look at what those faults look like on a device, and look at how the impact of spatial positioning and EMFI actually affects what faults you get out of it. Does this work for?
Right.
Let's see. There we go. Okay. So yeah, so there's kind of three main topics of this. The EMFI tool I'll introduce quickly. I'll then talk about how I actually did the on-die measurement using a TDC. And then I'll use that TDC to compare EMFI, voltage FI, and BBI, body biasing injection, which we just saw a talk on, to compare what the actual faults look like on the device, and how these different injection sort of platforms or technologies change what happens on die. So EMFI, so the first part's on EMFI tooling. In general, we have this situation where you have a strong magnetic field that gets injected or generated over a chip, which generates a voltage on the die, which then inserts our fault. Typically, the three kind of architectures, and this is a rough split, that you find used are either this direct drive EMFI. So direct drive on the left two, I'm calling it because the capacitor bank that generates the high voltage is directly switched onto the probe tip. So the probe tip is this inductor here or here. And the difference is you either have a high side drive, which is the furthest left. With high side drive, your capacitor bank is connected to the high side of your probe tip. This is easy technically to design for because your electronic switch, in this case, this MOSFET symbol down here, is always relative to ground. So your trigger input is relative to ground. This is really nice. This is easier to do to generate a trigger signal. The downside is that your probe tip is always exposed to the high voltage, so it's generally pretty dangerous. Another way of doing this is doing a high side switch. So in this case, what you do is your switch goes in between the high voltage and the probe. This is much safer because your probe that you might be able to touch is only exposed at the moment the pulse comes across. The problem with this is that if you start looking at the schematic, you realize that your trigger signal is relative to the switch ground, and that switch ground is going with the pulse itself. So you need circuitry that drives that signal and then follows the pulse. So this is pretty tricky to do. The plus side is that it's a lot safer. The other way that you can do this is you can have a coupled design. So with a coupled design, you generate a pulse and then couple it into the probe, normally with a capacitor. So there's a good paper exploring this, and this is intrinsically a lot safer because your high voltage flows through a capacitor, so it can't just be connected to the probe tip to shock someone. The only downside of this situation is that you have some, in this coupling, you kind of have this RLC circuit that's built here. So you have to do a little more tuning of the matching between the probe and that coupling capacitor. With the kind of direct drive systems, you're more directly generating a high current pulse that gives you your electromagnetic field. So, the different architectures have different trade-offs. The direct drive has some more flexibility on the probe tip, with the big disadvantage was that if you want the classically safe output, you have to have this really complex drive logic. So PicoEMP kind of uses the lower cost, easier drive architecture. It instead generates an inherent safety by having an isolated drive. So it uses these transformers that go between for both the high voltage generation and for the trigger generation. And so basically your trigger signal runs through a transformer. And so all this design's all open source, so you can go right now and download it, and people respun the designs already a bit. But this is the basic idea of PicoEMP as you use this inductive drive to fundamentally give you a safer output. To drive PicoEMP, the other half of it, so the name comes from a Raspberry Pi Pico, little microcontroller that generates a pulse width modulation for the transformer and generates a signal for actually giving you the glitch itself. But you can drive that from anything, so you don't have to use the Pico to drive it. This is just makes it even lower cost and easier to use. So it physically looks something like this. So the left side here is the high voltage. There's a shield that goes over the high voltage side. And so this makes sure you can't touch anything in there. And then once that shield's in place, everything on this side, so that output connector is electrically isolated from every other exposed point. So there's no way for current to flow from the output probe back to anything else you're touching. So if you touch it as a human, it's inherently safe, which is kind of the idea of PicoEMP. It's a low-cost tool, but it's also a reasonable teaching tool because you can use it without worrying that people are going to shock themselves. Just as kind of an aside, so the gate drive stuff is, I think, kind of interesting. So you basically have this lower part of the waveform here. You have a transformer. The big issue with driving MOSFETs or IGBTs or anything is that if the voltage gets too high in the gate, you get this punch through problem where basically you blow up the MOSFET because it overloads this very thin oxide layer on the gate here, which then destroys the device almost instantly. And they're very, very sensitive to this. So that's one of the problems with any sort of drive circuitry. And so the PicoEMP uses a pretty low cost resistor and Zener diode solution. And you can see the waveform here looks pretty nice. Like, so this is 10 volts, which is basically what you want to get up to. So 5 volts for division, you can see down there in the bottom. And you can see it pretty quickly rises to 5 volts. It's a little slower on the drop off. So PicoEMP obviously makes a number of trade-offs. And one of them is that the drive isn't as fast. The other main trade-off is the recovery time slower. It's a very small transformer that recharges a smaller capacitor than other commercial tooling. As an example, Chip Shouter, it's a new AE product I also designed that uses a high side drive. As a order of magnitude, the drive circuitry cost in this alone costs more than all of PicoEMP because it has to do that high side drive that's very complex. So the waveforms are a little sharper, but it's still, is somewhat comparable. You can get reasonably narrow pulses with PicoEMP. And more importantly, as I'll show you, you can actually get effective results. So the first result, which is a little more empirical here, is to run RSA from a Python library that's susceptible to the classic fault attack on the CRT portion of it because it doesn't check the output. And so this is Python running on Linux, running on the Raspberry Pi, not like bare metal or anything. And injecting and just all default speeds, nothing weird with that. And using PicoEMP, injecting it. And so the chips on the back side of this seemed to be a good position for injecting it. And what you see is that about 25% of the time you get a successful fault, which is pretty reasonable for this kind of setup, right? That's not especially fancy. About 30% of the time you get no impact at all. So the device continues operating without generating a faulty signature. And the rest of the time you can see is mostly application crashes, which again makes sense because there's no timing that's being done here. RSA is running in a loop and you just hope you hit roughly the right spot within it, which most of the time it's doing something you can glitch, so that makes sense. Yeah, but it is a pretty effective fault. And so you can see this tool even works on like a real system on a chip type thing, not just small microcontrollers. All right, so that's kind of part one. Part two, as I promised, there's sort of three things here, is looking at the time to digital converter. So this is a commonly used method of observing the analog waveform on chip. So there's been a number of papers that have used TDCs to explore waveforms on device. Really quickly, TDCs operate on the idea that you have some latch elements here. So these flip-flops. Between these latch elements, we have a very nice clock routing fabric, right? So this is the case in FPGAs and ASICs, you'd have something similar. The delay, the skew between these clock pulses is going to be very small. On the flip side, we can purposely introduce logic elements that have a little more delay, and that delay, like any digital element on the device, varies with voltage. So if we put in, for example, a rising edge here, the 0 to 1, you can see, depending on that delay, the one kind of makes it further along the latch because we assume the rising edge all happens at the same time. And so as the delay changes, we basically see more of these latches latch in a 1, assuming they were initialized to 0, right? Then if the delay is very short, then maybe it only makes it to the first 2 elements. So we basically have this scale now between the number of 1s that get latched in and what the voltage is, on the delay elements on die in the device. So this way we can actually measure what our glitch looks like to the digital devices we're trying to glitch. Oops. Yeah. On the ICE40, normally when these are done on FPGAs, they use a carry. So this SB carry is a element within the ICE40. Basically what it is between the different logic elements in the FPGA, they often have this special carry logic. The carry logic is designed when you're implementing a counter and you want very low latency between the carry logic between the counter stages. So they're kind of optimized for this because a lot of FPGA designs try to have high speed counters. So this is commonly what you use because the theory is, this delay is going to be smaller. It's easier to route between logic cells because it has this optimized routing. So when we look at this delay element here, this kind of looks like a ripple counter or something. So that's the reason we often see that SB carry or the carry. SB carry is the ICE41 in particular, but that carry element used. It's not the only thing you can use. So you can use general logic like the LUT, the lookup tables in the FPGA. So I also explored what that looks like on the ICE40. So on the left here is what the voltage supply is. So just varying at 100 millivolts. And then on the right is the average delay and the variance of the delay through that carry element. And I did that for the carry element and the LUT4. So the LUT4 is your standard lookup table. And it's sort of what you expect, but also, again, interesting to prove. The carry has a smaller variation with changes in voltage than the LUT element, which is also interesting because if you want to detect very small variations, so I'm doing this for glitching where we have pretty large variations. If you were trying to do this for side channel analysis, right, that might be a different story. And you actually may want the delay that changes more drastically with very small variations. So one of the other things that I hadn't seen kind of explored before was just looking at the different options you have within a device for building the TDC. So I'm going to use the carry because, again, for our purpose, this is better. This gives us a wider range of voltage. We expect to have pretty large pulses that we're seeing internally. A few elements get built around that. So this is also open source if you want to look at the actual implementation. What you have is there's a calibration delay. And what this does is this basically tries to put, when I said like, oh, depending on that delay, the 1 gets further along. As a default, right, we want to get about halfway. So we want the 1 to be reaching about half of the logic cells. And you just change the number of delay elements to do that. And this is really nice on the ICE40. It has an open source tool chain you can use for building the FPGA. So you don't need any crazy configuration logic. It just rebuilds the FPGA in a few seconds, reprograms it, and so you can optimize that really quickly. The output gets sent to an embedded block RAM. A single block RAM is used to minimize the chance that you glitch any of the state machine within this. Again, we're trying to glitch the device without glitching the TDC itself, just glitching something else that we're writing in it. So there's kind of this trade-off between making the design robust and having a lot of features or having a larger sample size. So in this case, the one limitation is it's limited to the maximum size of an embedded block RAM for how many samples it can take. And then that gets downloaded over SPI. Yeah, so that's what I said. You can rebuild the TDC in seconds. You can then generate. So this is kind of what your plot looks like. So it's very linear. Again, you expect that, but it's nice to prove. As you adjust the voltage, so this is if I adjust the external voltage, I look at what my TDC output is. And from this, we can also build a kind of calibration curve that I'll use in the next slides to show you what do the waveforms look like on die using actual millivolts, not just arbitrary measurements. So the other thing I do in the paper too is the TDC is really nice for an FPGA. It's not so nice for a microcontroller or other devices where you can't implement arbitrary additional logic, right? If you could add whatever logic to a microcontroller, there's a lot more you can do. So one of the other points was, what else can we use to help with our sort of glitch calibration and to use some of the outputs of this paper? To do that, I also attached an oscilloscope to the voltage rail of the device to observe the glitch impacts measured, just outside the device package, but in a way that you can do on any device. So that was the other points of this too. Yeah, so this is physically what it looks like. So there's an ICE40 on here. So this was a chip whisperer target, but you can use icebreaker. You can use a ton of different ICE targets. This one I just chose in part because it also had the voltage measurement set up right there, low noise, things like that. So that made it a bit easier. This was the PicoEMP is on top. And so that's then triggering pulses into the device at the same time as I'm measuring external signals. To actually test not just the impact of the TDC and just get waveforms, I want to know at what point do the glitches actually do anything useful. Two different targets are used for that. So there's a hardware AES implementation that another guy jumped here who did the tutorial this morning has ported to the ICE40. And so I use that implementation as part of kind of standard chip whisperer demos. So it wasn't designed for this work, but it's a good demonstration of a hardware target. For a software target, I used a RISC-V soft-core Neo RV32. Again, this is a public soft-core implementation. And on the RISC-V, I ran like a standard kind of loop test to understand, at what point am I seeing useful glitches without corrupting, too much, corrupting the FPGA or crashing it fully. So that was kind of the goal, is to see what are useful glitches, what do they look like, on the internal power rails, and to prove that I'm actually doing something besides just making pretty waveforms. For those devices, so when I do these practical tests, just quickly, what happens is the device has the practical like hardware AES core in it. It then gets reloaded, so it glitches it. We find the useful glitch. Those same glitch parameters are then used with the TDC core then reloaded. Nothing physically changes. So in this way, it's pretty confident, right, that I'm getting a very similar, there might be tiny variations due to the core itself changing. But it's basically first find a useful glitch and then measure that glitch with just the TDC core loaded. So that's how that measurement is done. All right, so the third part, results. As an example, hardware AES, so again, for each of the three things, so for EMFI, for voltage glitching, and for BBI, the parameters are adjusted until a useful glitch occurs in the hardware AES operation. At that point, I measure both the internal and external measurement of what the glitch parameters look like. And one of the points of this is that, if you're using a measurement, can you use that to help tune your glitch, even if perhaps either you couldn't observe the output or it's very slow to observe the output. And the interesting thing, so a few points here quickly, right? You can see in all three cases, we get sort of similar-ish waveforms on the internal power rails. Voltage glitching, we see a lot more ringing, for example, than EMFI or BBI. But both EMFI and BBI are actually generating sort of a drop in the internal power supply. So it sort of suggests that all of these methods do have some similarity in what they're causing happen internally. For the RISC-V core, it's a similar story, although we do see more variation. And again, the parameters here are just changed until I see useful glitches. And then we adjust what the useful glitches, and then we observe what they look like. So for BBI, we see these like two kind of lower pulses that aren't quite as pronounced on the external measurement. So, and part of this is you can sort of see this lower part that's dipping down, and then the release, there's quite a bit of ringing. So I'm assuming this is, you're seeing kind of the initial pulse application that's longer, and then the release of that, the ringing. For both of these, they are right? If you compare the hardware AES and this RISC-V core, you'll notice they're physically, longer and larger glitches on both the external and internal measurements. So we can also see the relationship between the internal and external measurements with this. The other thing we can see is, so with EMFI, right, there's this idea of the pulse width is one commonly kind of reported parameter. The pulse width, of course, itself doesn't directly mean we're inserting a fault that entire time. Really what we're doing is we have a rising edge here and a falling edge here, right? And it's the rising and falling edges that generate our change, that generate our inserted glitch. So that's what we'd expect. So again, we can observe that with internal and external measurements. It's most obvious at the bottom here. So if I'll start here with this 1 microsecond wide pulse, with the external, you can sort of see, right, there's a pulse here, and then one, so that's at 0.4 microseconds, and then 1 microsecond at 1.4, there's a pulse here. The internal measurement, because of that limited sample size, it just cuts off the kind of 1 microsecond point. But you can see it's starting to rise up. So it's more obvious with this 500 nanosecond, right? We see a negative pulse and then a positive pulse 500 nanoseconds longer. This is with PicoEMP, so this also matches, right, the other thing, and I should have used the PicoEMP figure there, but if you look at that figure, when I had the PicoEMP waveform, you'll notice that the rising edge is much sharper than the falling edge is much, much slower here, so a slower slew rate, which then also matches the fact that we see a stronger pulse one way and then a smaller pulse the other way, because of course the magnitude of this pulse we expect to be more related to the rate of change than it is to any absolute value. So we have a fast rising edge and a slow falling edge. And we sort of see this here. We get a strong positive pulse and then a much weaker, or a strong negative pulse and much weaker positive pulse. So that also matches. And eventually, if we make the glitch narrow enough, these two edges kind of combine and we instead get a smaller internal spike in the device. So it also shows that, the EMFI width is really impacting when these two positive and negative pulses get inserted, and the sharpness of the edges defines the magnitude of the pulses within the device. The final part that I think is actually maybe the most interesting too, is I also took a look at, with the same parameters on the same device, and just physically moving the EMFI probe around, what does an effective and ineffective glitch look like? So it's very common. We have these nice graphs that say, I got resets up here and a normal here and a glitch successful here. If I take those, and in this case, I always had the same RISC-V core loaded. So I didn't measure the internal, I just measured the external, but we saw that relationship in the previous slides. And so at the top is a successful glitch. Right, so a successful glitch. In the middle is an ineffective, aka nothing happened, just responded normally. And the bottom is the device reset. So from the top to bottom is kind of what you expect. You see the reset pulse is much, it's a more powerful looking glitch. What's interesting is that this middle one, the normal one, you see the polarity actually switches. And I didn't switch the polarity of the probe. All I did was physically move it around. Right, and this kind of matches because if you look at other work that have talked about the simulation of this, what you can expect is that you have these loops that are being coupled into, and if we think of our chip surface as not a perfect grid, it actually makes sense that as we move the probe around, we're going to get areas where we have better coupling. We have a larger loop that generates a stronger internal pulse, which also explains why there's points where I get a more powerful pulse and a weaker pulse for the same input settings. And even inverting the pulse, because if the loops go in the other directions, then we also might get that. There was a related kind of interesting work that implemented a whole bunch of TDCs on an Artex A100. So that's referenced in the paper too, and you can actually kind of generate maps of, for a given pulse, what does this look like on a device. So there is some related work here as well. To explore this, but I think it's pretty interesting to show that just by measuring the external power rails of the device, I can understand what the EMFI is actually doing on my device. Yeah, that's quickly an overview of PicoEMP, which is this low-cost EMFI tool that does try to focus on sort of safety-focused design to make it easier to use in a lab with students and things like that. Related, there's an open source TDC that focuses on an ICE40 implementation. The ICE40 is great, so if you haven't used it, there's a number of very cheap dev boards for it. So IceStick, Icebreaker are a couple of them. There's an open source tool chain, so it makes it really fast to reload designs. And with that, you can actually do these sort of tests to demonstrate, the link between EMFI, voltage glitching, and BBI, because the ICE40 is available in a wafer level device, so you don't have to decap anything to do BBI. And finally, by linking the internal and external power measurements, we can use the external power measurements, which are something you can do on any device, whether or not it has a TDC, to understand, how, as I move my EMFI probe around, how strong is the pulse being coupled internally? Is it inverting? Things like that. So I think with that, if there's any questions or